In this video, we'll talk about this headphone amplifier, which is essentially a revamp of a headphone amplifier I designed a couple of years ago. You might remember an older video featuring a headphone amplifier which had massively paralleled NE5532 op amps as a power amplifier. Since this design was a couple of years ago and there's a couple of improvements I could have added to it, that's exactly what I've done. And this is the NEXT version 2. NE because of the NE5532 and XT Extreme because this is, as far as headphone amplifiers go and schematic design and circuit design, this is pretty much overkill. Paralleling op amps like so to use them for example in output stages or even in preamp stages has quite a few benefits, including noise reduction, driving capability and so forth. I designed this board in Altium Designer, and this board was then manufactured and assembled by JLCPCB, so luckily I didn't have to assemble all of this stuff myself. We'll go through all the way from this power circuitry design up here. So we have an on-off switch, we have a DC barrel jack, kind of a stop-start circuit, a linear regulator, the LM317. We have various different inputs. So this coax input jack or this 1/4 inch input jack. And this jack is actually switched. So once I plug in, for example, a 1/4 inch cable here, stereo cable, TRS cable, this will then disengage this coax connector. So you can choose what input source you would like to use. From the input, this is then fed through this preamp section, and keep in mind this is stereo, so we always have mirrored sections. So there's one side, for example, left and right, and same for the power amplifier later. This is a very simple preamp using a Baxandall volume control, and I'll link you to a video on how that works because I've discussed it in a previous video with this dual gang, so stereo potentiometer. So the Baxandall's volume control is actually quite an interesting circuit, and we'll just go through it briefly. With this power on LED, and then finally, which looks quite impressive I think, this power amplifier stage, which is essentially per channel, so left and right, a load of these NE5532 op amps paralleled, and keep in mind per SO8 package there's actually 2 op amps, so 1, 2, 3, 4, 5, 6, so there's 12 op amps driving this output. So completely overkill for driving normal headphones, but why not give it a try? And then we have this 1/4 inch output jack, which then you can connect to your headphones. You can see these kind of bank of parallel 1210 SMD capacitors. I've used these instead, so this is about 1400 microfarads of capacitance. Because this is a single supply amplifier, so I'm biasing all of these op amps of mid-rail, and to remove the DC bias, I'm using these output capacitors just before the output stage. This is a 2-layer board, so if I turn this around, you can see the bottom is pretty much ground. I've done some small jumper traces, try to keep them as small as possible so I don't break up this ground plane too much. Just add some silk screen, and you can see this was November 2021. This normally runs off 18 volts, but goes up to 22 volts, and then regulates that down to, I believe, 15 volts to drive all this op-amp circuitry. So let's move over to Altium Designer and look at the schematic and PCB design in detail. Here's the previous video I did on an NE5532 headphone amplifier design, and this is the PCB we looked at. We looked at the circuitry in quite a bit of detail, and a lot of the detail I won't be showing in this video, and I would ask you to refer back to this video if you're interested, for example in learning how this Baxandall volume control works, which is pretty much one of the centerpieces of this design. But you can kind of see the evolution of also the PCB design from, I don't know, this was about 2 or 3 years ago when I came out with this, to the one which was last year. So quite a few changes, a couple of improvements, so let's go through that. As usual, thank you very much to JLCPCB for sponsoring this video. Both PCBs, the one from the first NE5532 headphone amplifier video and the one you are seeing in this video, were both manufactured and produced by JLCPCB. All the SMD parts were also assembled by them. If you would like to get your hands on one of these PCBs, either fully assembled with a case or just the Gerber files and assembly files so you can get them manufactured for yourself, I would please ask you to go to phils-lab.net. This is my website, and then go to contact and just shoot me a message regarding what you require. Thanks a lot. A huge thank you also to Altium for sponsoring this video. In pretty much all my designs these days I use Altium Designer, and I've also made this NEXT version 2 headphone amplifier purely using Altium Designer. If you'd like to try out Altium Designer for yourself, you can go to altium.com/yt/philslab. And you can get an Altium Designer free trial as well as 25% off your first purchase. So here we are in Altium Designer, and I've split this schematic up into 3 different groups. One is the power section, which contains power supplies, filtering, bias generators, and so forth. One is the preamp schematic, which essentially is the input filter, input buffer, Baxandall volume control, as well as a pre-driver for then the power amps. And the power amp section is over here with all of these massively paralleled NE5532 op amps. So let's go through one by one, just kind of glossing over the schematic. As you can see, there's nothing too complicated about it. The main features are this backsander volume control, which is pretty cool, as well as loads of paralleled NE5532s for output drive capability, reducing distortion, reducing noise, and so forth. As I stated at the beginning of this video, this headphone amplifier board is powered by a nominal plus 18 volt single supply. And this is usually what I take from some sort of DC wall wart, so I'm not using any AC to DC conversion here, which means we have to take special care with when it comes to biasing and so forth. I feed the main power in from, for example, a DC wall wart with a DC barrel jack, and this is anywhere between 18 and 22 volts, some sort of TVS diode for ESD protection, reverse polarity protection, which is typical, a P-channel MOSFET, a Zener diode just to clamp the gate source voltage, and that's pretty much it. I'm using this power switch because I want to use an on-off switch on my board, which I'll show you in just a second, and I don't want all of my current and all of my power essentially running through this on-off switch. So that's why I'm using this power switch, which has an input, an output, and an on-off control. But the nice thing about this power switch is this also has a current limit, as well as a soft start, which is pretty neat. So you limit your in-rush current. After all of this kind of protection circuitry, I come to my main filtering stage. So all of this stuff over here, the reverse polarity protection, power switch, and then the filtering is going to be very close to this DC barrel jack when we come to the PCB layout and routing later. Then a fair amount of filtering using this pi filter, so a farad bead, various bypass capacitors, and then feeding into a bog standard LM317 linear regulator. We require an input-output differential of about 3 volts for this thing to work properly, so the output is going to be about 3 volts lower than the input. And since we're using nominally 18 volts at least, and going up to 22 volts, and we want a 15 volt output, we're pretty much safe for that. All of this circuitry here, is in particular R1 and R102 and R103 are to set the output voltage, and the rest is pretty much protection in the form of these diodes, as well as an additional soft start circuit. Lastly, before we feed this onto our main supply rail, I've added the option of adding in additional filtering. Again, this called a pi network, but this, instead of using a farad bead, I'm just using a resistive element instead. In this case, I've just put parallel 0 ohm resistors because I don't want to perform any filtering, and if I have any noise issues, I can replace these resistors with higher value resistors. You can see I've paralleled them just for power handling and thermal capabilities. And then my 15 volts essentially powers the rest of this board. Just below, we can see this on-off switch, which then divides down the input voltage and then feeds that to the power enable signal of this power switch. Also, of course, some sort of power on LED, and that's about it. So starting to talk about biasing, I'm using bias generators for the left and separate for the right channel to bias all of my remaining op-amps in the preamps and in the power amplifier stage. So all I'm doing is I'm dividing my 15 volts in half. So at this node here, I'll have 7.5 volts because of these equal valued resistors. I'm performing some sort of filtering in combination of all of these components, and I get a kind of cutoff frequency of about 15 Hertz. Then I use paralleled unity gain voltage followers and coupling their outputs together with 10 ohm sharing resistors. And this provides my bias voltage of really rock solid stable bias voltage at 7.5 volts for all of my left channel. And all this circuitry is then simply mirrored for the right circuitry. This means I get less crosstalk between these left and right channels. And that's all there is to the power circuitry, so very, very simple, even though it looks like there's quite a few parts to it. Moving on to the pre-amplifier, we have RCA jacks as well as a 1/4 inch jack as our input source. So this might be some sort of computer output. It could be from a tape deck and any source you can pretty much think of. Again, some sort of ESD protection. This 1/4 inch jack does switching, so once I plug in something into this 1/4 inch jack, this essentially disengages the RCA jacks. Then I have ESD protection, of course, and R200 in combination with C200 and a tiny bit R21 and R202 are there for RF filtering. So before we hit any substantial nonlinearities, that is any semiconductor elements which might demodulate any RF present on the input, I perform some sort of RF filtering. Just R200 and C200 give me an RF filter cutoff of about 1.6 MHz, and of course any source impedance coming from this side on the left will decrease this cutoff frequency. The main determining factors for the input impedance of this amplifier are R201 and R202 in parallel, so 22K in parallel gives me about 11 kilo ohms. Then we just simply have a unity gain voltage buffer, and then feeding into this backsander volume control. So essentially you're using a linear dual gang potentiometer. So with one potentiometer, we're essentially controlling 2 wipers because we're using a stereo system. So the top part of this potentiometer feeds into the right channel over here. But we're just looking at one channel to start with, of course. I won't go in very much detail in this video of how this backsaddle works. In the previous video, I've already explained how this backsaddle tone control works, and it's quite a cool and elegant concept. Essentially what we need is another unity gain voltage follower, followed by the main amplification stage, and our amplification factor is given by R206 divided by R204. So 5.6 divided by 1, so a gain of 5.6, which in dB is 15. C208 is to limit the high frequency response, so in parallel with R206, this is a low-pass filter. Also, just a note on biasing, you can see R202 is poured to the V-bias left supply, and the right channel will be poured to the V-bias right supply. In this way, this node, buff in left, sits at half the supply voltage, which is 7.5 volts, and which means this NE5532 op-amp has a maximum possible voltage swing, input and output. Because we're biasing, we don't want this to disturb the source, and we don't want the source to disturb the biasing, and this is why I have a C201 in place, which is a series coupling capacitor. And I've chosen this C201 in combination with input impedance to give me a high-pass filter of about 3 Hz cutoff. And typically I would choose my cutoff frequency to be about 10 times lower than, for example, the band I want to be in. So if I want a 20 Hz audio band starting from 20 Hz, I want about 10 times less than that. 2 or 3 Hz is perfectly fine. So continuing on, after the backsaddle stage, we couple onto a pre-driver, I'll call it, just for simplicity. And this is inverting and unity gain. So you can see I have equal resistors at R207 and R209. And this is because the backsaddle volume control is naturally inverting the phase, and I'm just reverting it back to be essentially in phase, so to speak. Not strictly needed, but it's also good to have a pre-driver because we're driving quite a lot of op-amps after the section. And that's all there is to the preamp. So RF filter, ESD protection, biasing, backsaddle volume stage, and some sort of pre-driver and phase inversion. And we're doing the same thing identically for the right channel. So left and right are always going to be identical. And that brings us to the last page, and rather overwhelming looking page of the power amplifier. Again, left and right are mirrored. And this is incredibly simple. Instead of just using one operational amplifier to drive headphones, which it probably would struggle with, one of these NE5532 op-amps can drive, quite a decent amount of power into about a 600 ohm load. And given that we might want to go down to 32 ohms of the headphones as a headphone load impedance, I've paralleled, quite a lot of them, 1, 2, 3, about 12 of them in parallel, and I'm sharing the outputs using these 1 ohm current sharing resistors. So they all tie together to the same node, and again, because this node and the whole op-amps sit at half the supply voltage for maximum voltage swing, I need to use DC blocking capacitors. So I could use, a huge electrolytic capacitor that I put, which I did in the previous version, but I've gone the fancy route, and this does have its benefits using ceramic capacitors instead. That is the right type of ceramic capacitors. And I've just paralleled quite a lot of these together to give me about a total 1400 microfarads of capacitance, together with a 32 ohm load, for example 32 ohm headphones, which might be these small earbud type headphones, give me a cutoff frequency of 3.6 Hz. Left and right channels, identical of course, that just gets fed to an output jack with ESD protection, and that's pretty much it. So as you saw, the schematic is pretty straightforward, albeit very much overkill and pretty much just purely out of interest. I actually stole this idea from Douglas Self, who wrote many good books on audio electronics, and he made a proper power amplifier, so for large hi-fi speakers, using exactly this technique, and this is where I got it from. So layout-wise, this is a 2-layer board. You can see the 3D view in Altium here. The bottom layer is a ground plane. I'm trying to have a thin 2-layer board, so if you can go with 0.8 millimeters, that's what you want, because you want close coupling between the top layer and the bottom layer, and 0.8 millimeters is pretty much as thin as you can reasonably get it on a 2-layer board without adding cost. I've just sectioned those off, so I have the power section all together, everything spaced out, so the preamp isn't interfering with the power amp, the power supply section isn't interfering with the power amp, or the preamp, and so forth. There's not much to pay attention to other than spacing when it comes to these hi-fi or audio amplifier designs. So trying to keep spacing between critical traces, that might be the input traces and the power amplifier section and so forth. Another point is that you should place your decoupling capacitors or bypass capacitors close to the power supply pins of your operational amplifier. You can see I've also designed this PCB to fit in a custom 3D printed enclosure, so I've included 4 mounting holes, as well as placed my input and output connectors fairly reasonably at the front and rear of this PCB. This way I can also make my own custom front and rear panels for my enclosure. I've tried to put power together, then the input sources on the back of this PCB, and at the front of the PCB I have my headphone output, my power on LED, and then my volume control over here. So there's nothing too crazy going on with the layout. I've tried to keep things nice and tight, and I won't go into too much detail about this. This is a pretty simple design. What I'd like to show you, however, though, is I also made front and rear panels, which I also then had made at JLCPCB, and these are simple 2-layer boards. And these days you can get them made out of aluminium or just the usual FR4 fiberglass. So I used 3D CAD modeling software to then get the exact positions, and because I had 3D models for my connectors and switches, this is pretty easy to do. So we have all the cutouts for the 1/4-inch jack, the coax, power, switch, and all the mounting holes which then go into the chassis, and I've just included small slots for cooling. And in 3D, you can make this quite cool because you can get a black solder mask PCB with a white silkscreen. Similar for the front panel, I had some made as well. Appropriate holes for the power on LED, volume control, potentiometer, and headphone jack, as well as the 4 mounting holes. So thank you very much for watching this very brief walkthrough of the NE5532 NEXT V2 headphone amplifier. I hope this gave you some inspiration to maybe try something like this for your own designs. If you're interested in all things audio electronics and discrete designs using transistors, op amps, and so forth, I can really highly recommend Douglas South, who is a British audio engineer. And I myself have quite a lot of books by him, in particular these 2 books, and I can really recommend. So Small Signal for preamp design and so forth, and of course this power amplifier design book, well worth the money. So thank you very much for watching, and I'll see you in the next video.